Can you hear me? My name is Amir Shalom. I'm from Vibra in Israel, and I've come to give a lecture about how we implement performance at a very, very large scale here at Vibra. But before I start about the backend that runs all of our system, I'd like to give a little bit of an introduction about our company. So Vibra was founded about 4 years ago. It started as an iPhone application for free voice over IP calls. And after a few months, an Android version was released and text messaging was introduced. Since then, we've added many new features, and now we're a media communications platform supporting almost all mobile phones, tablets, and desktop operating systems. In the beginning of the year, we were purchased by Rakuten, so that's why I'm here. Let's talk a little bit about the Vibra Service. The Vibra Service provides reliable text messaging, giving you indications when a message was sent, received, and even when the other person read the other message. Your message that you sent to them. We support group platforms of up to 100 different people, and we allow all of our media information to be sent to these 100 different people, which includes pictures, videos, doodles, stickers, and many other features. We also have a feature called Push to Talk, which allows sending your voice while you're talking without even waiting for the recording to end. If you do this, for example, with a group conversation, then you can instantly broadcast your voice to up to 100 different people at once. So it's a very nice feature. And of course, we offer the initial voice features, allowing for both voice communication, voice calls, and video calls, which we added recently. Since the beginning of the year, we've already also started to monetize the Vibra service. We still have most of the initial features which are free. It will always be free to continue to text and provide voice calls. But we've added premium services which you can get at a very, very low price. The first service that we added is Vibra Out. Vibra Out allows you to perform voice calls from Vibra to a regular phone number, either a landline or a mobile number, and this does this at very, very low and competitive rates. The second feature, Sticker Market, which allows you to send or purchase sticker packages. We have different sticker packages, either free or premium paid sticker packages. Each sticker packages has different pictures, like you can see in the picture here. We have both branded content like Smurfs, Garfield, things like that, and also our own characters such as Violet, Eve, Blue, Freddy the Fox, and others. The Vibra service is very, very simple and easy to use. We use your phone number as your registration ID, so you don't have to make up a username or things like that. You just put down your phone number, and immediately you're registered into our system as a unique user. You can also add additional devices, multi-devices, such as your tablet or desktop devices. You can add as many as you want. All will be registered under the same single phone number and completely synced between them. That means that every single message that is sent to a certain device, or a certain phone number actually, will be automatically sent to all of these devices at once. We also have all of your devices are always on and connected to our servers. So this will allow us to give you very, very fast service. Within a fraction of a second, every message is sent to all of your devices. And we're able to do this without sacrificing your battery life. We've also have localized versions of Vibra for over 32 languages. And additional multi-device features, for example, that we have, if you receive a phone call, for example, it will ring on all your devices at once. Let's say you answer on your mobile phone, and then you arrive home and you want to transfer it to your desktop. With a push of a button, you can transfer the call. While you're talking, the other person doesn't even notice. It rings on your desktop or laptop, and you can answer, and it will seamlessly transfer the call to the other device. So it's a very nice feature. Also, all of your messages that are read on a single device are automatically shown as read on any other device you have. So everything is very, very nicely synced between all of these devices. Let's talk a little bit about the numbers behind Vibra. As I said, Vibra is a very, very large service. We have over 400 million users in our service, and over 1 million are added every single day. So as I said, it's growing very, very fast. We're sending billions of messages every day and billions of talking minutes every single month. Now, I've been giving similar lectures like this throughout the year. In the beginning of the year, when I had this slide, it said about 200 million users. In the middle of the year, about 300 million users. And now, we're over 400. So we are growing and continuing to grow extremely fast. Just to show you how we're growing in 2013 versus 2012, we've grown in talking minutes about 3 times, in messaging about 5 times, and in group messages 12 times within a single year. You can see here the graph. This is an actual graph according to the months since 2011. A little bit after we started until the end of last year. And these are the messages per month, and you can see just how fast we've been growing. So now let's talk about the database architecture working behind the scenes to push all of these billions of messages to hundreds of millions of users with sub-second latencies. The database architecture had a few generations. It's not the same architecture today as it was when we started in 2011. In the beginning, as I said, we were a very small startup creating a nice little application for an iPhone. We didn't know what we would be today, so we started out having our Vibra clients connecting to our application servers, and in the back end we had a small in-memory database that was actually brought from another company that we had, and it was basically a single server doing in-memory database solution. This was working nice for 2-3 months maybe, and since we were growing exponentially and very, very fast, we found that this solution was simply not good enough. So we searched for a solution which could both be very, very scalable, but which could be implemented very fast as well, because we had to replace it while we were growing. So we looked into NoSQL technology, and we wanted a sharded NoSQL technology. At that time in 2011, there weren't many options. The solution that we picked was Mongodb, which at that time didn't actually have an official sharded NoSQL release, and we were actually using their initial beta version of their first version, which supported the sharding. And I think we were, if not the biggest or one of the biggest solutions for MongoDB at that time. So we moved to the second generation architecture. Again, we have our Vibra clients and application servers. Everything is on Amazon Web Services, all of our servers. And initially, we had only our MongoDB cluster on the right there. The MongoDB had a master and 2 slaves. So we had 3 copies of the data. Again, we were working on Amazon, so nodes can fail all the time. So that worked nicely for some time, few more months. And then we found that, again, it was not giving us enough speed. So we found that we had to have a caching solution in front of MongoDB. So we added Redis, which is a very, very fast in-memory database solution. It was configured in a master-slave configuration, and that was giving us much better speed. Again, a few more months passed, and the master-slave solution for the caching simply wasn't big enough. We had too much data, and we couldn't find a server on Amazon that would give us enough space for the cache. Unfortunately, Redis does not support charting. It only supports a master-slave configuration. So we basically built our own Redis charting solution to allow us to distribute data across multiple shards of Redis. So we then had our MongoDB cluster, our Redis sharding cache in front of it, which again lasted for a few more months. Then we found that MongoDB wasn't giving us enough performance. The performance we were getting from MongoDB, because of its persistency layer and speed, wasn't fast enough, and we started creating an additional Redis sharding solution, a sharding cluster, which had data in addition to Mongo. It wasn't only a caching front. It was actually a completely different cluster, which would hold data on its own, with basically very limited persistency, as Redis is an in-memory database. But simply, we didn't have a fast enough solution otherwise. So then we understood that this database architecture wasn't giving us what we needed, and we had to find another solution. This architecture wasn't without its advantages. It did, in fact, get us through the first few years of extreme growth, which is very important, of course. We never actually lost any data from MongoDB. We had many database failures and node failures, maybe even downtime, but we didn't lose any data from the MongoDB. Redis performance was extremely well. Redis is a lightning-fast database and works very, very, very well in terms of speed and performance. But of course, as I said before, it had quite a few problems. The main one was the performance of MongoDB. MongoDB was giving us somewhere in the ranges of tens of thousands of operations per second, which at that time we needed hundreds of thousands of operations per second, and it was simply impossible to get it no matter how big we increased the size of our MongoDB cluster. We have hundreds of application servers, each one with multiple working threads. They would all connect to a single MongoDB cluster. Now, MongoDB, for each connection that was connected to it from an application server, would have a separate worker thread and stack, which would require a lot of memory and CPU. And when you scale it up to hundreds of application servers, with multiple worker threads, it would simply be very, very wasteful and put a lot of pressure on the MongoDB cluster. So it was very difficult to scale it up to the size that we needed. Redis, as I said, is an in-memory database solution, so it had very, very limited disk persistency and very bad robustness. It also did not support sharding, so we had to use our own sharding solution, which was not a commercial-grade sharding solution, so it had problems. It was not manageable. It was very difficult to use. And it was simply not good enough for what we needed. We needed a commercial-grade database sharding solution which we could use. So that's why we moved to a third-generation database architecture. Now, what were our requirements for such an architecture? First and foremost, we needed very, very high performance. As I said, hundreds of thousands of operations, today in the millions. We work with very, very large data sets. Almost every data set that we use is in the billions of keys. And it was in MongoDB, for example, we found that when we had billion keys or multiple billions of keys, it would also hinder performance greatly. In Redis, for example, this would work fine. We needed a scalable solution. As we were growing and continuing to grow very fast, we needed a solution which we can add nodes while everything is working very, very easily without interfering with the performance and the system that's working. We needed a robust solution. Everything is on Amazon Web Services. That means nodes are virtualized, nodes can fail, and we need something that can withstand these kinds of problems and failures as they are happening all the time. We also need a system which can have, we'll call it a configurable level of robustness. We have certain clusters which have more important data, for example, and we have those which have less important data, which can be redundant data, caching data, things like that. So we need different levels of robustness, different levels of replica settings, for example. We need a system that can be backed up. In case of, let's say, a full failure of a database, we needed an option to be able to restore it in case of a catastrophe or something like that. So we need a backup solution which could back it up every day, every week, something like that. Our system is always on. That means we can't turn it off for an hour to back it up. We can't turn it off for maintenance failures, hardware upgrades, software upgrades. Everything has to be on all the time during all of these maintenance requirements. It's very, very important to be able to monitor your database. So we need a very good monitoring solution. Ideally, we need both the database itself to be able to provide some kind of internal monitor with a user interface and something which has an external API which can connect to our existing monitoring and alerting solution. And finally, we do prefer a single database solution. Before we had our persistent layer and we had our caching layer. Ideally, we would prefer a solution which would be able to do both in the same single database. The solution we chose was Couchbase, which is a NoSQL sharding database. And the third generation architecture looks as follows. We still have our Vibra clients connecting to our application servers. And then we have several different Couchbase clusters. We decided to separate them into a few different clusters. We have right now 6 different Couchbase clusters, which each one has different settings. We found that it's more efficient to have smaller clusters instead of one big one because different workloads have different ways that they work. Some are more read intensive, some are more write intensive, some have big data sets. So it's better if we have more optimized settings according to the different workloads of the databases. All of our servers and clusters working with Couchbase are SSD based for increased performance. So all their disks are SSD. We have different replica settings, so between 1 to 2 replicas. So every different cluster has at least 1 additional copy of the data, and some have even 2. So 2 different replicas means 3 total copies of the data. In addition, we have our backup cluster on the right there, which is using XDCR technology, which is a cluster replication technology, which replicates data across different clusters. We have a separate cluster for several reasons. It doesn't replicate all the data that we have in our clusters, only the most important data, which will allow for, in case of a catastrophe and the whole cluster goes down, we can basically go over and move to this backup cluster and have all of our operations work from this backup cluster instead of the main cluster. In addition, in Couchbase, since it's a key value database, if we want secondary indexes or different indexes or searches, views, data analytics, things like that, they have a special view technology, but unfortunately this works from disk and not from memory. and also put some performance issues on the database. And we prefer not to put those on our main production databases. So all of these secondary indexes, views, and things like that are done from the backup cluster. And we also have on the bottom there, I called it a backup. We basically back up all of our, or most of our clusters on a daily basis. We basically compress them and upload them to S3. So we can always, if there is a very big failure of the whole cluster, which still hasn't happened, fortunately, that we had to use them. And we can basically go to S3, take a day-old database, and restore it. Now, migrating from the second to third generation databases was not an easy task. We have to migrate a live system, which means that we have a system which is doing hundreds of thousands of operations per second, receiving millions of users all the time, new users. And we have to do this and migrate from one database to another while everything is happening. We're not allowed any downtime at all, not even a minute. So we can't say, OK, we'll turn this off and turn this on and copy the data. We can't do that. We have to do this everything while everything is running. We can't allow for any data loss. As I said, we're working on Amazon. So during this migration period, nodes may fall and have fallen. And we have to be able to do this migration, taking this into consideration, and be able to work with failures of nodes while they're happening. We have to make sure that the data is consistent. The migration process is a process which could take a few weeks. That means a single database entry could be updated a few times during that time. And we have to make sure that everything is up to date at the end of the migration process and has the most updated copy of the data. So how did we migrate? There were several stages to perform this type of migration. In the beginning, in stage 1, we basically added a new Couchbase cluster. Now, as I said, we had several different Couchbase clusters, so we didn't do this all at once. We did this 1 or 2 clusters at a time. We added the new cluster to the existing system and only deleted keys from the Couchbase and continued working with the other one in parallel. The second step was to continue reading from MongoDB. MongoDB was at this time the single source of truth still, and only write and delete data to both of them. So every new update from stage 2 and up was updated on both Couchbase and MongoDB. Stage 3 was to basically a background process, which would copy all the data from MongoDB to Couchbase. So basically, we would export all the data after stage 2 and start importing it into Couchbase if it didn't exist. That's why it's important, for example, to have stage 1, which would delete the keys. Because moving from stage 1 to 2 would still take time, as we have hundreds of application servers and we don't restart them all at once. We do them one at a time. It could take a few hours. So there would still be application servers, some on stage 1, some on stage 2, and we have to make sure everything is staying consistent. After we finish loading all the data that we exported from MongoDB into Couchbase, we have a validation process to make sure that all of our data is valid. Every single data element that we imported into Couchbase, we log. And we also log all the data that's exported from MongoDB, and then we compare those. If there's errors, we check them. If there's any inconsistencies between the keys that we exported and those imported, we get a list of them. In addition, we also do random checks of a few tens of thousands of actual values to make sure that everything is consistent. Until this stage, we can basically stop everything, throw the whole Couchbase cluster in the garbage and start everything again. At this stage, still MongoDB is the single source of truth, and we can always go back to that. And we actually, one of the clusters, when we migrated to it, we actually did have to, in the middle, stop everything and start all over again. What we had is, almost a year ago, we started using in Amazon the i2 instances. We were one of the first customers to use that. And unfortunately, they had a problem with their virtualization layer in Amazon. And they started restarting their instances every few hours. So we had a database which would start restarting nodes every few hours. And even worse than that, because they use multiple tenancies on a single node, they would happen a few instances at once. So basically, in the middle of this migration stage, we started having instances restarting like crazy. And what we did is we stopped this process, went back to Mongo, worked it out with Amazon, and then started all this process again. So it's very important to be able to go back to the beginning without losing any data. Okay, stage 5, we start moving to Couchbase as our source of truth, and reading from Couchbase, and still writing to both Couchbase and MongoDB. As I said, this needs to be in a separate stage, as we have multiple application servers which are not restarted at the same time. And finally, we can remove MongoDB and start using Couchbase. Now, what's interesting is that this process of migration, I think, is more difficult process than the actual usage of Couchbase itself. So it was more difficult to plan and write the migration process than actually using and writing the whole layer of the database itself. So this is a very, very complex process, which, as I said, had to be done about 6 times because we had 6 different clusters, and a very delicate area. It also puts a lot of strain on the application servers because during this process, we basically have to write everything twice. We have to write everything both to Mongo and to Couchbase, which increases the latency and the load on the application servers. So it's very, very important to plan these stages very delicately. Here we can see a Couchbase cluster with 60 nodes during the migration process. You can see in the first half, you can see that the load is much higher. The number of sets per second is around 60,000 sets per second. This is in March when we did the migration for this cluster. And when at the end of this migration process, when it's finished, you can see that it goes down into a nice sine wave of daily usage, and is working much more regularly than before. So you should make sure that during the migration process, you can see there's a much, much heavier load on the database, which it has to do. This cluster also, as you can see, has a lot of items. It has about almost 7 billion items, so it's quite a large database. Now, the backend servers that run Vibra, we have over 500 application servers right now. The second generation database architecture, which we worked with, had a MongoDB cluster, a single cluster with 150 different servers in a master and 2 slave configurations, so 3 copies of all the data. We had a Redis cluster, or 3 Redis clusters actually, with a total of 144 different servers in a master and single slave configuration. Now, the MongoDB configuration, the master and first slave were SSD-based, and the second slave had a regular EBS. The third generation database architecture uses 7 different Couchbase clusters, one of which is the backup cluster, which the largest cluster is 60 nodes. We have between 1 to 2 replicas for each cluster. A replica is an additional copy, so we have between 2 to 3 copies of the data. We use XDCR on some of our clusters to the backup cluster. That's the cluster replication technology. And we have our external daily backup, which backs everything up to S3 in case of failure. Right now we have a total of less than 200 Couchbase servers. So on total, you can see that we have increased database performance with less servers and less money. A few interesting facts about our usage of Couchbase. We've recently doubled all of our Couchbase instances. As I said, we are growing very, very fast. So between the beginning of the year, which we did the migration, until now, we had to double our capacity size. In order to do this, we had two options: either double the cluster size or double the size of each node. In this case, we decided to increase the size of the nodes because we didn't want to grow to very, very large clusters. It's usually better to use clusters which are not over about 60, 70 nodes. So as we were more or less at the limit, we decided to increase the sizing of the clusters, the actual nodes, sorry. In order to increase the size in Couchbase, basically what you have to do, if you have a certain bucket size, you can't have a mixed bucket size across different nodes. So what you have to do in order to increase the size is that you have to basically add additional nodes which are double the size and rebalance them in, which is a feature of Couchbase. It's called rebalance, where you add a new node instead of another node while everything is working. It takes usually between 30 minutes to 2 hours, more or less, depending on the size, every rebalance. So the first stage is to add all these new nodes in to the cluster with the new size. Once all the nodes are at the new size, basically then you can increase the size all at once to all the nodes at once to be double the size. But you can only do this when all of the nodes have been replaced. And then you increase the size and you have a bigger cluster. And usually in the beginning, you might want to even remove a few nodes because if you don't want double the size and you want, let's say, 1.5 times the size, you would still have to, at the first stage, double the size, and then you can reduce the number of nodes. The total number of operations that we do right now, more or less, is about 1.5 million database operations per second. So we're doing quite a lot of DB operations. It's not spread evenly across the clusters. As I said, we have our 7 clusters. The backup cluster is basically not doing almost anything. And then we have our 6 other clusters, which are doing between 20,000 to, I think the biggest one is about 650,000 operations per second for a single database cluster. Now, in contrast to what you might think, the bigger clusters are not necessarily doing the bigger operations per second. Actually, the 2 biggest clusters are doing the lowest amount of operations per second. The one doing the most operations per second is, I think, a 21 node cluster. The bigger ones are basically because they're holding more data. That's why you need the bigger clusters. In Couchbase, in terms of speed, as I said, it's a very, very fast database. So even a smaller cluster can do these hundreds of thousands of operations per second. In order to achieve these high speeds, the higher performing clusters have all of their data in memory, both the active and replica set of the data. Everything is 100% in memory. So that allows for very, very fast speeds. If you want a very, very fast database doing hundreds of thousands of operations per second per cluster, you don't want any disk reads. The disk reads, it can still work in the tens of thousands of operations per second, but if you want these lightning fast speeds, everything has to be in memory. Here we have a relatively small cluster, a 12-node cluster. You can see here that it's oscillating between about 100,000 to 350,000 operations per second on a daily basis. This is from a few days ago. You can see there on the top right, it has over 3,000 vbuckets. In Couchbase, you have every copy of the data has 1,024 vBuckets, a virtualized bucket, which is spread across the cluster. So if we have 3,000, that means we have 3 copies of the data, in this case, an active and 2 replicas. We have a little over 2.5 billion items in this case, and everything is 100% resident in memory. This cluster is also replicated using the XDCR to the backup cluster. In this case, you can see that about 1.6 billion mutations have been replicated. That means the number of keys. And the more interesting thing is the latency between the clusters is a little under 1.5 milliseconds. So that means the backup cluster is about 1.5 milliseconds in delay of the main cluster. Now, the backup cluster is using the cluster replication. The replica set, which is the copies within the cluster, are updated much, much faster than this and are done in microsecond latency, usually. So everything is working very, very fast. Usually the latencies that we're seeing in Couchbase, internally, at least on the server side, are in the level of microseconds. So usually the network latency is much, much higher than any of the internal server latencies. So as I said, everything must work very, very fast, even on the smaller clusters and especially on the bigger ones. So that's my lecture. Yes?
When did you actually do the migration? Oh. When did you do the migration from Mongo to Couch? Was that this year or was that a year ago?
The migration started basically, I think about a year ago. It started the Q4 2013. And it ended somewhere in the beginning of summer, I think, of this year.
Got it. Okay.
Any other questions? Yes. Yeah. Let me go back to the slide where I showed that, and I can explain. Okay. The migration stages, the reason I did the first stage, as I said, the application servers are not updated between stages all at once. We have over 500 application servers. It takes usually a few hours to restart them. They're usually restarted every few seconds, one after the other, so we can continue working during the upgrade. So basically, we have several application servers on, let's say, stage 1 and several on stage 2. Now, in stage 3, basically, we do the background copy of the data from Mongo to Couchbase, but only if it doesn't exist. That means that I have to make sure that a data element is not in Couchbase if it's not supposed to be. Now, let's say somebody is in stage 2 and writes something to Couchbase, and still some of the application servers are in stage 1. In stage 1, if I delete a data, I have to make sure that it's also deleted from Couchbase so that stage 3 knows that it has to copy the data if later on it's copied. So it's a little bit tricky, but that's the reason we have that stage in the middle. Yeah, any other questions? Yes?
Do you know what your capacity is for your third generation, and what's coming up in the fourth generation?
Capacity in what terms?
So have you done some stress testing on this to know what the maximum capacity of this platform is?
I don't know exactly what the maximum capacity performance that we could maybe achieve from this. Usually, the main factor that requires us to increase the size is the sizing of the database. As I said, the most what's limiting of the Couchbase usually is if we want higher performance, we need everything in memory. So basically, what's limiting is that we have to fit everything in memory, and that's usually what makes us increase the number of nodes in our case. So as I said, lately we doubled the size. That should give us a few more months. And we can still double the size again. We're one before the highest size. But we can increase also the node count, of course, increase the sizing of our clusters themselves and make them bigger. Also, Couchbase is all the time improving their service. Right now we're using Couchbase version 2.5.1. Recently, I think about a week or 2 weeks ago, they released a new version, version 3, which has some improvements. So we're working very closely with them in order for them to add very important features for us to be able to work with the requirements that we need in the future. Yeah.
Can you tell us a little bit about redundancy and cross-geographical replication and distribution of your nodes?
Okay. All of our database clusters are in the same Amazon region. They are spread across different availability zones, though. In Amazon, you have different availability zones, which are in different data centers, and are in case one goes down, a second one would, in Amazon at least, they said it would never go down another one. They have different, let's say they're connected to different power grids and internet connections and everything, and they never did actually have an event where two different availability zones within the same region have gone down. So in terms of robustness, spreading across different availability zones should be enough. Now, in Couchbase, one of the features that we did work with them very closely in the beginning last year, they still didn't have the feature, and one of the things that we waited until we moved to Couchbase is the rack awareness or zone awareness feature in Couchbase, which allows you to spread the replicas to different availability zones. So all of our clusters are spread evenly across 3 different availability zones, so that even if a whole availability zone goes down, Couchbase makes sure that the replica or the copy of the data is in a different zone itself. So we had a few weeks ago, there was this big Amazon issue that probably you read about or heard about, and they brought down about 60% of our servers. And one of the things that was important, that they made sure that every day they only brought down a single availability zone. So that's why we were able to work throughout this problem without any database failure at all. Yes?
Do you find any issues with Couchbase or any problems that you guys face working with Couchbase?
Problems with Couchbase was the question. Couchbase has been working very, very well. Again, it's not a perfect database, as anything is. One of the things that we found, for example, a problem is that it is limited a bit in terms of scalability and node count. As I said, you usually don't want to go over about 70 nodes per cluster. It's usually counterproductive, and it doesn't work too well. Another feature that is limiting for us, at least, is that Couchbase requires you to use either a Couchbase bucket or a Memcache bucket. In the Couchbase bucket, you have to use persistence to disk, and in a Memcache bucket, which is a memory only, it doesn't support rebalancing. So if you use a Memcache bucket and then you change the number of nodes in your cluster, you basically lose data during the rebalance. As Memcache in the Couchbase terms is only a caching layer. So we would like, for example, to have a feature which we would have a Couchbase bucket with only an in-memory solution without persistence to disk, which is not available there. Any other? Yes.
Yeah, when you looked at choosing Couchbase and comparing Mongo and Couchbase, I mean, I'm not that familiar with Couchbase, but it seems to me like there aren't as many installations at scale of Couchbase. Can you talk a little about what did you learn in terms of how prevalent is Couchbase in terms of number of companies or installations at scale versus MongoDB? And do you have a sort of an opinion on that?
When we did look for Couchbase, the Couchbase solution about a year ago, MongoDB was much bigger and more available than Couchbase, and I think we were one of their biggest installations at that time, about a year ago. I know that today there are much bigger companies than us. I don't know how much. I won't be on Couchbase side. I don't want to say. I don't know who they can say and who not, what customers they do have, but I can say there are very, very big customers using Couchbase, and I know at least on the enterprise scale, I know that they have been growing very, very fast this year, and are, I think, one of the 3 biggest or 4 biggest companies in the NoSQL market today. Okay, so thank you very much.